Добрий день.
Добрий день, добрий день.
Здрасте. Не, не будет. Не.
Добрий день, шановні колеги.
Одна хвилина залишилась, і він. Все, уже можно починать.
Hello, dear colleagues. Let me to introduce Professor Kajita. Distinguished Professor Takaaki Kajita, dear international colleagues and partners from the universities of Aachen, Leuven,
Громче, громче, громче.
Mishkals, International University of Malaysia, Petroshan University, Warsaw, Poznan, Sofia Universities, and Otto von Guericke University of Magdeburg. I welcome everyone and I'm glad to see you all present at our events dedicated to the celebration of Science Day in Ukraine. As always in May, our university is preparing a number of events that bring together scientists, researchers, and popularization from all over the world to build a brighter future together. And even in the difficult time, the time of unproved Russian aggression, when Russian troops are preparing an attack on Kharkiv, we are here.
Да ясно. Ой, а тогда в подвале.
We are working and we want to support our dividends with our educational and scientific activities. Today will be a memorable day for all polytechnics because today a distinguished scientist, Japanese physics, leading researcher of the cosmic neutrinos and of the Nobel Prize in Physics 2015, Professor Takaaki Kajita will give a lecture exploring the universe, which neutrinos and gravitation waves for the scientific community of our university, Kharkiv and Ukraine. Takaaki Kajita is a dignitary university professor of the University of Tokyo. He was director of the Cosmic Ray Research Institute of the University of Tokyo from 2008 and to 2022. He was the president of the Science Council of Japan and until September 2023. Professor Kajita received his PhD from the University of Tokyo School of the Science in 1896 and has been conducting research at the Kamiokande and the Super Kamiokande detectors at Milwaukee Observatory in central Japan. In 1998, at the Neutrino International Conference held in Takayama, Japan, presented the results of the analysis that provided strong evidence for atmospheric neutrino oscillations. In 2015, he was awarded the Nobel Prize in Physics for his role in the discovery of neutrinos. In addition to the Nobel Prize in different years, Professor Kajita has received other prestigious awards. Currently, Professor Kajita is also the leader of the KAGRA projects, which aims to study the gravitational waves astronomy. Professor Takaaki Kajita is one of the 194 leaders of the Nobel Prize who in 2022 expressed their support for the Ukrainian people and the free and independent Ukrainian state in the face of Russian aggression. Takaaki Kajita is also a signatory to the letter against the regime, in which he and the other leading figures in science, economy, and literature made the appeal to the international community to increase support for Ukraine in its resistance to the Russian invasion. On behalf of the scientific community of Ukraine and in partner the National Technical University Kharkiv Polytechnic Institute, I thank you, Professor Kajita, for your higher moral principles, for your efforts, for the benefit of all people. I also want to note that Professor Kajita has already visited Ukraine in 2019, and he was awarded the title of Honorary Doctor of the National Academy of Science of Ukraine for the significant contribution to the development of science, social progress, peace, understanding, and cooperation between peoples. I would like to ask you, dear Professor Kajita, to begin your lecture.
Yeah, yes. Well, thank you very much for the kind introduction. Also, thank you very much for the invitation to this important event. Now let me share my slide. Okay, today I want to talk about neutrinos and gravitational waves. Well, actually, this talk is based on our researches. Therefore, this is not a general review of this field, but I just want to discuss what we did in our observatories. Okay, now this is the outline of this talk. First, I have a brief introduction on cosmic rays, neutrinos, and gravitational waves. Then I want to move on to neutrinos, Kamiokande, super Kamiokande, and hyper Kamiokande experiments. Then I want to move on to gravitational waves. And we are now trying to observe gravitational waves with the Kagura Observatory. So I want to discuss these activities, and I'll summarize this talk. Okay, let's begin. Well, slightly more than 100 years ago, Victor Hess measured the intensity of radiation at the balloon altitude. And through this measurement, he discovered that the intensity increased with altitude. And in fact, this was the discovery of cosmic radiation or cosmic rays. Because the intensity increased with the altitude, that means there must be some radiation from the space, and that was cosmic rays. And also, this discovery told us that excuse me, there are phenomena in the universe that cannot be observed with optical telescopes. And in fact, over the last 100 years, cosmic rays have been studied. And now, cosmic rays are a very exciting field. Cosmic rays, including high-energy gamma rays, neutrinos, and gravitational waves, are telling us the secrets of the universe. Now, in this occasion, I'd like to briefly introduce our institute, Institute for Cosmic Ray Research. This institute is basically a cosmic ray institute, and many researchers carry out observations of various cosmic rays. And in fact, we have various facilities and experiments outside of Japan. And there is a highest energy cosmic ray observatory in United States. And we are joining the CTA high energy gamma ray project. And also we have facilities in Tibet, in China, and also we have another facility in Bolivia, in the South America, sorry. Also, in addition, we have the Super Kamiokande and Kagura facilities located in Japan. And with these facilities, we carry out the studies of cosmic rays. So, in today's talk, I want to talk about the neutrino studies and gravitational wave studies in two of these facilities. Okay, now I want to discuss neutrinos. Well, I'm not sure if I need this kind of introductory slide, but let me, in any case,
вовремя поработала над своими ошибками.
okay, thank you. Let me introduce what are neutrinos. Neutrinos are fundamental particles like electrons and quarks, and neutrinos are, say, something like electrons, but without electric charge. And in fact, this has a significant consequence, and neutrinos can easily pass through even the Earth or even the Sun. And neutrinos can bring information of the fundamental processes at the center of the stars. And neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to mention that for many years, neutrinos have been assumed to have no mass. Before finishing this page, I just want to briefly tell you how we measure neutrinos. Of course, we can never measure neutrinos themselves, but, well, very rarely, a neutrino can interact with a nucleus, and in this case, typically a charged particle is produced. And, well, in fact, we have various ways to observe this charged particle. For example, if this charged particle propagates in water, then photons called Cherenkov photons are emitted, and therefore we can observe these photons by photodetectors, and therefore by observing these photons, we understand what happened with the neutrino interactions. So this way we observe neutrinos. Now, I want to discuss our experiment, our initial experiment, Kamiokande. Well, the history of neutrino studies in Japan started more than 40 years ago. The motivation is written here. About 50 years ago, in the 1970s, ground unified theories of elementary particles predicted that protons should decay with a lifetime of about 10 to 30 years. Well, this means if we observe proton decays, that is a very strong indication that the idea of grand unified theories are right, and therefore several proton decay experiments began in the early 80s, and one of them was the Kamiokande experiment. Well, here I show the sketch of the Kamiokande detector. It was a large water detector. We constructed a large cylindrical water tank in underground. It had about 16 meters in diameter and 16 meters in height. And it contained 3,000 tons of very clean water. And with the 3,000 tons of water, there must be a lot of protons, and therefore some of the protons may decay at that time. And then typically 2 or 3 particles could be emitted, and therefore these particles should propagate in the water and then emit Cherenkov photons. Therefore, the idea was we should observe Cherenkov photons produced by the proton decay with these photodetectors installed in the inner side of the water tank. So this was the idea. Of course, we have to construct a detector, and the detector was constructed in the mountain area in Japan. And in fact, the Kamiokande detector was constructed in an active mine. And the photo in the right side shows the members of the Kamiokande who worked for the construction of the Kamiokande detector. And you see in the middle, there's Professor Koshiba, who was the leader of this experiment. And in fact, he received Nobel Prize in Physics in 2002 based on neutrinos, observation of neutrinos in the Kamiokande detector. Well, the actual construction work was like this. I said the Kamiokande tank was 16 meters high, and we needed to install the photodetectors onto the detector wall. Therefore, the issue was how we install the photodetectors onto the detector wall. And in the end, we decided to use these plastic boats to install the photodetectors. So, well, we worked for several months to install the photodetectors. And in fact, you see there are 3 people working on the boat. And in fact, one of them was me. And in fact, I enjoyed these works very much. Also, I was excited because I thought that the data from Kamiokande may tell us the secrets of the universe. So around that time, I decided to be a physicist. Well, actually, at that time, I was the first year PhD course student, but well, I was really excited and I decided to be a physicist. Unfortunately, the real proton lifetime was much longer than predicted by the grand unified theories in the 70s. So we didn't observe proton decays. However, Professor Koshiba realized that the photomaterial tube or photodetector used in Kamiokande had a very good sensitivity. And therefore, he thought maybe boron-8 solar neutrinos whose energies are around 10 MeV could be observed in Kamiokande. Well, of course, there was a reason that Professor Koshiba proposed to observe solar neutrinos in Kamiokande. At that time, there was a famous problem called the missing solar neutrino problem. The measurement result by the Homestake experiment in United States suggested much fewer solar neutrinos than predicted by theory. Therefore, many people thought that the missing solar neutrino problem must be due to some problems in either the solar model or in this experiment. Therefore, Professor Koshiba thought it's very important to have an independent solar neutrino experiment to tell if there was a problem in the experiment. So Professor Koshiba proposed to improve the Kamiokande detector to observe solar neutrinos. Well, we worked to improve the Kamiokande experiment for several years. And finally, at the beginning of 1987, we started the stable observation of low energy events. Then something unexpected happened. Here I shows two photos of Large Magellanic Cloud. One is before the supernova explosion, and another one is after the explosion. And clearly you see there was a very bright star after the explosion. This was the supernova SN 1987A at the Large Magellanic Cloud. And as I said, at that time, Kamiokande started the stable observation of low energy events. And therefore, Kamiokande looked at the data and immediately found we observed neutrinos from supernova. And here I showed the summary of the neutrino observation by 3 experiments: Kamiokande, IMB, and Baksan. Well, in total, there was only 24 neutrino events. But these 24 events were enough to understand the basic mechanism of the supernova explosion. Namely, we understood when a massive star finishes its life, the star collapses, a shock wave is generated, and the outside of the star explodes. So with these 24 events, we confirmed the basic mechanism of the supernova explosion. And for this observation, Professor Koshiba received Nobel Prize in Physics in 2002. Also, this event told us that neutrinos are very important. And therefore, the Japanese government approved the construction of the Super Kamiokande experiment. The Super Kamiokande detector is a very large version of the original Kamiokande detector. It is a 50 kiloton water Cherenkov detector. It has about 40 meters in diameter and 40 meters in height. And in fact, this is an international collaboration. We have about 230 collaborators from these 11 countries. Well, the Japanese government approved the construction of the super Kamiokande detector in 1991, and immediately after the approval, we started the construction work, and it took us about 5 years. And well, in fact, at the beginning of 1996, the construction was almost finished, and we started filling pure water into the super Kamiokande detector. So this photo was taken at that time. Now, with this detector, we studied various neutrinos, and one of them was the neutrinos created by cosmic ray interactions in the atmosphere. When cosmic rays come into the atmosphere of the Earth, they interact with air nucleus, and typically, after the interaction, pions are created. Of course, pions are unstable and decay to other particles, but muon and neutrino, and muon is also unstable, therefore decay to an electron and 2 neutrinos. So you see, during the decay chain of pion, 3 neutrinos are created. And these neutrinos, well, most of them simply pass through the Earth, but some of them interact in the super Kamiokande detector. And we observed and studied these neutrinos. And of course, the motivation was to study if neutrinos oscillate. Well, more than 50 years ago, several theorists predicted if neutrinos have mass, neutrinos change their type from one type to the other. For example, as shown in this figure, if a muon neutrino is created at 0, then begin to propagate to the right, then at some point, the probability that a muon neutrino remain as muon neutrino goes down, and at that point, tau neutrino is appearing. But this neutrino, if it still propagates, then at some point, the probability that muon neutrino to remain muon neutrino come back to unity. If they propagate further, then the probability go down, come back to unity, go down, and so on. So this is neutrino oscillations. Therefore, this was theoretically predicted, and therefore we wanted to confirm or observe if neutrinos really oscillate. In fact, today I didn't prepare any slide, but before super Kamiokande, Kamiokande had some hint of neutrino oscillations. Even in Kamiokande, we observed atmospheric neutrinos, and at that time, we found that there's a deficit of muon neutrinos. In Kamiokande, we were unable to find the reason why there's a deficit, but clearly, neutrino oscillations could explain the data. And therefore, we wanted to know if neutrino oscillation could explain the deficit of muon neutrinos observed in Kamiokande. In fact, we accumulated data and we made this plot. This shows the number of mu neutrinos observed as a function of the zenith angle, and cosine, well, theta is the zenith angle, and cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos. And these neutrinos came from the other side of the Earth. And the black circles with error bars show the data, and the hatched histogram shows the simulation. And in the simulation, we did not include neutrino oscillations. Then you find that for downgoing neutrinos, the data and simulation agreed reasonably well. But for upward-going neutrinos, the data showed essentially a factor of 2 deficit compared with the simulation. And this data can be well explained if we assume neutrino oscillations, namely muon neutrinos created in the other side of the Earth must propagate in the Earth before interacting in the super Kamiokande detector. But they have to travel really a very long distance, typically 10,000 kilometers. Therefore, during the propagation in the Earth, they change their type from muon neutrino to tau neutrinos. And therefore, when they arrive to the super Kamiokande detector, the probability that a muon neutrino to remain muon neutrino is just 50%, as data indicate. So this was the discovery of neutrino oscillations in super Kamiokande in 1998. Well, of course, we reported this discovery at the neutrino conference, as introduced at the beginning. Then, well, something unexpected happened. President Clinton in the US gave a talk at MIT's 1998 commencement. And, well, during this talk, he mentioned about the discovery of neutrino oscillations. Let me simply repeat what he said. He said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Of course, as the US president, he mentioned in Super Kamiokande, there are many Super Kamiokande collaborators from US, and therefore there are a lot of contributions. In addition, he mentioned the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, well, clearly, we were very much honored to hear this kind of words from the president of a country. Well, nowadays, we understand some of the presidents of some countries are not like this. Well, but anyway, let's move on. Well, certainly it was really an honor to hear this kind of words from the US president, but you may wonder why the US president was so excited. Why physicists are so excited? Well, indeed, we are excited. And let me tell you why we are excited. And here I show the mass of elementary particles. There are three types of charged leptons, electrons, muons, and tau. And the mass of these particles are shown by red colors. In addition, there are 6 types of quarks. Quarks exist inside the nucleon, proton, or neutron. And the quark's mass are shown by green and blue colors. Well, now, after the discovery of neutrino oscillations, we have been working very hard to understand the neutrino mass itself. And indeed, I think we understand the mass rather well now. And let me plot the neutrino mass. They are here. Well, the horizontal axis is the mass, and you see that 1 unit is 100. So from this figure, you find that the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. More than 10 orders of magnitude smaller than other particles' mass. Very small, extremely small. Well, because of this extremely small mass, we are excited, and we believe this is the key to better understand elementary particles and the universe. And in fact, if we understand why neutrino mass are so small, we certainly understand elementary particles better. But in addition, we think that these small neutrino mass might be the key to understand the universe better. Let me tell you why we think so. Well, this is a photo of the far universe. We see many galaxies. And, well, there's one thing we know. These galaxies are made of matter particles. There's no antimatter galaxy. Well, it seems this is just trivial. However, if we think about the history of the universe, we find this is not trivial. At the beginning of the universe was extremely hot. And in this extremely hot universe, always particles and antiparticles are created simultaneously. Therefore, at the beginning of the universe, the number of particles and antiparticles should have been equal. Then, with the universe cooled down, particles and antiparticles meet and annihilate, disappear. Therefore, now, if we think this way, we do not expect any remaining matter particles in the present-day universe. But clearly, the data indicates there are many matter particles remaining. Why? Well, to be honest, we do not know exact reason yet. But there are theoretical ideas, and one of them indicates that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So we are excited, and we'd like to check if idea is correct. And therefore, the neutrino community has been seriously working to check if possibility is correct. Unfortunately, the present neutrino experiments are not powerful enough. And therefore, we need the next generation neutrino facility. And with these next generation neutrino facilities, we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. If the difference is observed, we believe it will be the first step to understand the origin of the matter in the universe. And in fact, at least there are two next generation neutrino facilities which are under construction, and one of them is Hyper-Kamiokande. Hyper-Kamiokande will be the next generation neutrino experiment. It will be about 8 times larger in the fiducial mass. And the experiment is under construction. And well, in fact, at present, well, it is in the excavation phase. A very large underground cavity is under excavation, as shown in the bottom right photo. And experiment will start in 2027. And this is actually an international collaboration of about 600 people from 22 countries and regions. And I want to thank the Ukrainian physicists to join this Hyper-Kamiokande project. Thank you very much. Okay, now I would like to move on to the next topic, that is gravitational waves. Well, gravitational waves were predicted by Albert Einstein in 1916 based on his theory of general relativity. Well, to be honest, at the time of Albert Einstein, he was not sure if people can observe gravitational waves. But after his initial prediction, black holes were predicted. In fact, nowadays, we knew there are, in fact, black holes in the universe. And if the black holes are the binary system, forms a binary system, then these two black holes orbit each other. And from this system, we expect strong gravitational waves are emitted. And if gravitational waves are emitted, then the energy is released, and therefore these two black holes come closer and orbiting faster and faster. Then finally, the two black holes merge. A newly heavier black hole is formed. And also, you find that gravitational waves are propagating to the outer space. So we'd like to observe these gravitational waves. Then the question is, how shall we observe these gravitational waves? And well, in fact, the effect of gravitational wave is the change of the length. Due to gravitational waves, the length between two objects may shrink or get longer. Therefore, we'd like to observe this effect. And for this, we use laser interferometers. Here's the laser, and then here's the beam splitter, and half the beam go straight, and half the beam is reflected to this way. And there are mirrors reflecting back the light. And then there should be an interference at the beam splitter, and the interference light is observed in the screen. Well, in fact, let me explain. So this is the idea. Well, of course, light is a wave, and therefore, so wave is reflected back by the end mirror. Then here's the interference, and typically the interference light is minimum at the screen. However, by some reason, the length to the end mirror is changed. Then the interference effect is observed in the screen. So this way, we direct to observe gravitational waves. Then, well, you may ask, what kind of science we'd like to do with by observing these gravitational waves? Well, at least we'd like to study these phenomena shown here. One is the merger of binary neutron stars, and with the observation of gravitational waves of the merger of binary neutron stars, we'd like to understand the origin of the heavy metals in the universe. Well, of course, we know, say, heavy metals such as gold. But, well, until recently, we did not know where these gold are generated in the universe. Also, with the observation of the binary neutron star mergers, we'd like to understand the inside of the neutron star. In addition, we'd like to observe the merger of binary black holes. And in fact, as I will discuss briefly later, we have been gravitational wave observations indicate that these black holes are rather heavy, heavier than observed by X-rays and so on. And we do not understand why we observe so many heavier black holes than expected. Maybe gravitational waves observations indicate that the first generation stars, but we are not sure yet. So we'd like to observe more the binary black hole mergers. And finally, we'd like to observe the supernova explosion. And certainly the gravitational wave data must be very important to understand how the heavy stars finish their life. So these are things we'd like to study with gravitational waves. And in fact, already almost 10 years ago, actually on September 14th, 2015, LIGO observed the signals in their two laser interferometers. The data told us that two black holes of 36 solar mass and 29 solar mass each merged at the distance of 1.3 billion light years, newly forming a 62 solar mass black hole. In the right top corner, I show the data at that time, and clearly you see the wave pattern, and you see green curve and red curve agreed quite well. And in fact, blue one and the red one agreed quite well. And these two curves came from two independent laser interferometers. So we think this was really a great discovery. The gravitational wave astronomy was born at that time. Well, that was 9 years ago. Since then, LIGO and Virgo, LIGO in United States and Virgo in Europe have been observing many gravitational wave events. This is a summary of the gravitational waves observed before 2023. Well, in total, there are 90 events. Oh, by the way, blue circles show black holes, and orange circles show neutron stars. So the data told us that most of them are binary black hole mergers, but there are several binary neutron star and neutron star black hole mergers. So, well, it's clear. There are many very important science with gravitational waves. Therefore, we would like to contribute to the gravitational wave astronomy. Therefore, we have been working hard to contribute to the gravitational wave astronomy, and we have been working hard to construct the KHGRA laser interferometer. And from now on, I want to discuss what we are doing in the KHGRA collaboration. By the way, KHGRA collaboration is an international collaboration. We have about 160 authors or 400 collaborators from 8 countries and regions. And you see many of the collaborators come from the East Asian countries. And this is the sketch of the KHGRA interferometer. KHGRA is located in underground in a mountain, and in the same mountain, there are super Kamiokande neutrino detector and other neutrino detectors. So, KHGRA is located in this kind of scientific mountain. And KHGRA is a 3 kilometer by 3 kilometer laser interferometer. Oh, by the way, before moving on, I just want to briefly tell you my personal history. Well, initially, I started my research on neutrinos. Then now I'm working on gravitational waves. Well, I want to tell you why I decided to change my research field. Well, I studied neutrinos for more than 20 years. And after the discovery of neutrino oscillations in 1998, and after some more studies for several more years, I was feeling that I finished what I should do in my neutrino research. Of course, there are many important topics in neutrino research in general, but I was feeling that I finished my contribution on neutrino research. On the other hand, there are still many exciting sciences that we would like to study. In particular, gravitational waves had not yet observed at that time. At that time means early in the century. And I was fascinated by the research on gravitational waves and the studies of the universe with gravitational waves. And in fact, in 2008, I was appointed the director of the Institute for Cosmic Ray Research. And at that point, it was clear that I could no longer contribute to neutrino research much. But still, I wanted to be involved in exciting research. Therefore, I decided to participate in the gravitational wave project, KAGRA, with my partial time. And since then, I have been working on gravitational waves. Well, I think we were lucky. KAGRA project was approved in 2010. Then we started the construction work. By the way, I want to mention, even the 3 kilometer by 3 kilometer tunnel was excavated. Then after the excavation, the first work was to install the 3 kilometer by 3 kilometer vacuum tubes in the tunnel. And the connection and the leak test of these beam tubes have been finished in March 2015. Okay, then we had to install many vacuum tanks, mirrors, vibration isolation system, and so on. So we worked in the essentially in the central area and end stations. In fact, as shown here, the central area is rather complicated. There are many vacuum tanks, and in each of the vacuum tank, we typically have one mirror suspended by vibration isolation system. And the installation is done in the clean room, and therefore you see many plastic seats. And in these clean rooms, we installed mirrors, vibration isolation system, and so on. By the way, one of the key features of the KAGRA laser interferometer is the use of cryogenic mirrors. Well, these laser interferometers are so sensitive, and therefore even the thermal noise of a mirror is a problem. Therefore, we decided to cool down the mirrors to about 20 Kelvin. And in fact, in order to cool down the mirrors, we have to be careful in selecting the material. And indeed, we decided to use sapphire for the material of the cryogenic mirrors. These mirrors are quite big, 22 centimeter in diameter and 15 centimeter in thickness, 23 kilograms. And anyway, these mirrors are installed into the KAGRA laser interferometers. And then after finishing these laser interferometer construction works, physicists came out from the underground and work outside. And in fact, the laser interferometer control and commissioning is carried out at the surface facility. By the way, today I mentioned the Kagura laser interferometer. However, I want to mention that the global collaboration of these gravitational wave interferometers is very important. Well, the scientific output will be maximized by the global network. For example, the pointing accuracy of the gravitational wave event will be much improved by the network of LIGO, Virgo, and Kagura. Well, as you may understand, any interferometer, any single interferometer, even if it detects gravitational wave, it cannot tell from where the gravitational wave came. If we collaborate worldwide by observing the signal arriving timing, we can tell the from where the gravitational wave comes. And therefore, we work together and Kagura joined the network observation in May 2023 for 1 month. Actually, at that time, we thought we do not have enough sensitivity to observe gravitational wave. Therefore, we returned to work for the sensitivity improvement, and Kagura was planning to rejoin the observation in the spring of this year, now. Then, unfortunately, there was a strong earthquake nearby, well, about 100 kilometers away from the Kagura laser interferometer. Well, indeed, this was a very strong earthquake, and the surface building was really damaged. But, well, I think we were fortunate because we installed the Kagura laser interferometer in underground. The effect of the earthquake was significantly smaller in underground. But still, there were many damages in Kagura. So we started the recovery work. In fact, this recovery work will take a long time. We hope that Kagura can rejoin the observation and contribute to the gravitational wave astronomy as soon as possible, hopefully in early 2025. Well, let's see. Anyway, so this is the status. Well, sometimes, well, this kind of earthquake happens, so we cannot control. So we have to work. Anyway, before finishing, I want to show you this slide. Well, today, I initially talked about neutrinos, and then I talked about the gravitational waves. So far, I completely separated these two topics. However, neutrinos and gravitational waves should not be completely separated. For example, if a supernova explodes at the center of the Milky Way galaxy, then we should be able to observe many neutrino signals. In addition, we should be able to observe gravitational wave signals. And if we combine the neutrino signal and gravitational wave signals, we truly understand the mechanism of the supernova explosion. So I think it's very important to work together. And this is the essence of the multi-messenger astronomy. Okay, let me conclude. Well, today I talked about neutrinos and gravitational waves. And I think neutrinos and gravitational waves are exciting scientific fields. And I believe many more fundamental discoveries will be ahead of us. And I have been very fortunate that I have been able to work on these research topics. Well, sometimes, well, unexpected things happen, but in general, I was very fortunate. And finally, I want to tell that this research have been possible because we have had a peaceful and free society. I hope that peace will be restored to Ukraine as soon as possible, and that we can work together in various scientific researches. Okay, that's all from me. Thank you very much.
Евгений Иванович, микрофон включи.
Да, включил. Thank you very much, Professor Kajita, the very interesting your report. And if you don't mind, we have some questions.
Yes.
Okay. Have you any questions to Professor Kajita? No. Just a minute.
Yes. Sorry. Yes. We have a question. First, our question: how do the thinking related to defect mass and anti-gravitation in black hole, and what's the role of this process of modern physics in general relativity? And what's the potential of application of your research for understanding our universe and future? Thank you.
Okay, thank you. I understand that your question is on gravitational waves, right?
Yes, it's correct. Yeah.
Okay. Well,
Have any questions?
certainly. Oh, okay. Let me answer to your question. Well, certainly. Well, we would like to understand the origin of the heavy metals in the universe, and also the origin of the black holes in the universe. And well, certainly this is just two examples of our research topics. And well, I hope that we can contribute a lot to understand various unknowns in the universe. Maybe my answer is just too general. Sorry.
Okay, thank you. We have one question in chat. What progress in research potential can be achieved if we build twice larger neutrino detector? If we will build, or if we will build 10 times larger detector?
Thank you. Thank you. In fact, this is an interesting question. Well, since the neutrino interaction is very rare, therefore, if we want to have more neutrino events, we need larger mass. If the mass is just twice larger, then we can only observe two times more neutrino events. And typically, 2 times more neutrino events is not enough to really improve our understanding. But if we have 10 times larger neutrino detector, then we have 10 times more neutrino events. Then, well, we believe we have, in fact, a very good progress in neutrino physics. In fact, well, compared with Super Kamiokande, Hyper Kamiokande has 8 times larger mass. Therefore, we expect there should be a big progress in neutrino physics with Hyper Kamiokande.
Thank you for your answer. And the next question, please. Okay.
Professor Larin, please.
Thank you very much for possibility to answer the question. Thanks, first of all, great thanks for a very interesting lecture. You know, all the materials are so comprehensive, it's so interesting and exciting how we could go deeply in understanding of physical particles and understanding of the universe and how it works. That's great. But being a member of technical university, I'm really interested in practical application of the possible usage of such knowledge, and not only to develop some engineering structure, but also to, let's say, organize our human behavior more reliable to the nature, to be more accurate in whatever they're doing in nuclear reactions, in different space journey, space using technology, and so on. So what could you say for answer on this a little bit philosophical question, but how this study or similar study could be used in the future for changing our behavior and also to use in engineering science?
Okay, well, thank you very much. Well, okay. Well, certainly the technology in neutrino physics and gravitational waves are quite different. Therefore, let me talk about the technology in gravitational waves. Well, at the beginning of the gravitational waves, I mentioned we need to observe the length change due to gravitational waves. However, the problem is the effect is very small. Suppose a gravitational wave comes to our solar system, then the distance between the sun and the earth change. Well, the problem is how significant is the change, length change. If a strong gravitational wave comes to the solar system, the distance between the sun and the earth could change about 10 to minus 8 centimeters, the size of the hydrogen atom. We have to observe this extremely small length change in our 3-kilometer arm length laser interferometer. So we have to use as many optical and other technologies as possible. Indeed, well, if we tune the laser interferometer very well, our sensitivity is limited by essentially by quantum mechanics. And therefore, our experience will be used in many future very precise technological applications.
Thank you for your answer.
Thank you very much. I also have, I'm sorry, I also have one small question. That's not from your today lecture, but I a little bit searched on this matter before your lecture, that to be more precise. And I figure out that in 2012 in US, there is an interesting research how they could use neutrons to send their message through the rock. I mean, to organize the communications. based on this very small, almost massless particles as a new level of information transition, perhaps in the future. What do you think about the possibility to use this type of theory from the communication point of view?
Oh, sorry, I have no idea. I'm sorry.
Okay. Thank you very much.
Thank you. We have several questions more. Stanislav Fedorchuk, please, you can turn on your microphone and ask your question.
Thank you. At first, thank you for so interesting presentation and so informative. I have maybe some kind of amateur question as a technical scientist. In the neutrino oscillation, is there some neutral state between mu and tau or not? Can we find this? Because in technical, I know about neutral state, so transforming, not immediately changing, but some neutral position. So please.
Thank you. Thank you for this question. In fact, this is simple quantum mechanics. But when we say, for example, a muon neutrino or tau neutrino, this means a neutrino interaction produces a muon, then that means this neutrino is a muon neutrino. And if a neutrino interaction produces a tau particle, that means this neutrino is a tau neutrino. Okay, now, since we have neutrino mass, then there must be mass state. And in fact, mass state and the usual neutrino type, muon neutrino and tau neutrino could be different. Actually, it should be different. For example, in general, muon neutrino could be superposition of two mass states, and this superposition of two mass states propagate in the vacuum, but of course the mass is different, and therefore the wavelength is different. Therefore, the relation between the two mass states, the initial state cannot be conserved at some point. Therefore, there must be some transition to other particles, that is tau neutrinos. So, well, okay, this is neutrino oscillations, but well, I am not sure if I understand. If I answer to your question properly.
My understanding is rising, so thank you for your answer. Thank you.
We have one more question. Gennady Shabanov, please turn on your microphone.
Thank you very much, Professor. Interesting lection. Forgive me for my understanding of this information, or if I interpreted incorrectly. As for, I want to ask from the beginning, as I could understand, the photodetector installed in superconductor register energy glow of cosmic rays. Yes, and this means you receive some sort of picture. Yes.
Yeah.
So this is a matrix of pixels, and you can receive a video photo of universe. Yes, understand correctly?
Yeah. Yes. Okay. Yes, we have the essentially array of photomultiplier tubes in the inner wall of the tank, and well, actually, if a neutrino interaction occurs in the water of the detector, then say charged particle propagate in the water, then Cherenkov photon is emitted, and the matrix of the photodetectors observe the photons, and in fact, the shape is kind of say round shape, and by analyzing this shape and the photon arriving timing, we understand what kind of neutrino interaction occurred, like that.
Thank you. Thank you.
And final question for today to Professor Kajita from Molnar Hanna. Please, Hanna, turn on your microphone.
Actually, I don't have any questions, but I want to thank you for this fascinating lecture, Domorik Dazimas, and wish good luck you with these researchers.
Thank you very much.
Dear colleagues, our time is dear colleagues, our time is finished, and I want to say very much for your very interesting report and answers for our questions, Professor Kajita. Thank you very much for your time and take part in our conference, and I hope that we continue work together in the future. Thank you very much.
Yes,
Bye-bye.
so, thank you very much. Bye-bye.
Sure.
Goodbye. Thank you for your presentation.
Thank you very much.
Thank you very much. And goodbye.
Goodbye, thanks.
Goodbye.
Thank you very much. Very interesting.
Goodbye.
Thank you very much. Thank you very much.
Thank you very much. Goodbye.
Thank you. Goodbye.
Thank you very much.